When a photon of light strikes the retina, it is converted into an electrical impulse and routed to the primary visual cortex. At this entry point, the signal represents a discrete sensory event, stripped of context or meaning. At this primary stage, the information remains isolated. The visual cortex identifies edges and orientation, but it possesses no data regarding what those visual features actually represent in the world. Survival, however, does not happen in a vacuum. To navigate the world, an organism must reconcile these visual signals with touch, balance, and its own internal physiological state. Classical models often depict the brain as a collection of isolated, walled-off compartments, but this modular view struggles to explain how these regions actually cooperate. We have to look past these static borders and toward interconnected networks. Modern neuroscience suggests that higher cognition is an emergent property of these widespread, dynamically interacting systems. It is the result of continuous communication across distributed neural populations. To understand how thought arises from biology, we must move beyond the search for a central processor and instead map the architecture of integration. This architecture follows the principle of hierarchical integration, where the brain builds complex representations by continuously layering and combining simpler data points. As information moves higher into the cognitive hierarchy, a specific biological constraint appears. The nervous system does not invent new computational mechanisms to handle sophisticated thoughts. Instead, the recurrent and distributed principles that govern raw sensation are simply scaled across broader levels of neural organization. This biological consistency allows us to trace a physical path from a local sensory map all the way to complex goal-directed behavior. We begin building our model at the association cortex, the regions that bridge the gap between sensation and movement. These areas act as hubs where signals from different sensory nodes simultaneously converge. This convergence allows the brain to combine inputs from multiple modalities into a single coherent representation. A primary example is the posterior parietal cortex, or PPC, which serves as a convergence zone for spatial awareness. Here, visual data merges with somatosensory touch, vestibular balance from the inner ear, and proprioceptive information regarding the body's position in space. The PPC does not just map external objects, it maps them in direct relation to the organism's body and its capacity for physical action. Reaching for a cup is not a purely visual task. It is an integrated spatial construct that requires the seamless merger of sight, touch, and physical self-awareness. While the parietal lobe maps space, the temporal association cortex focuses on meaning. Information arriving here becomes progressively detached from immediate physical sensation. It transitions from raw visual features into stable, abstract concepts. By integrating visual streams with stored knowledge, language, and emotional significance, the temporal cortex generates semantic meaning. To link these distributed concepts across time, the hippocampus draws connecting lines between these semantic hubs, spatial maps, and emotional centers. This suggests the hippocampus is not a static storage folder, but a system for rapidly forming relational organizations across the entire cortex. A memory, therefore, is the dynamic reinstatement of a network that spans the brain, rather than a file saved in a single location. The highest level of this cortical integration occurs in the prefrontal cortex, or PFC. The PFC is often described as a standalone central executive, but the biological evidence points toward a more integrated role. In our model, the PFC supports behavioral flexibility through continuous, two-way communication with sensory cortices, the hippocampus, and motor systems. To coordinate this massive data volume, the thalamus sits at the core, sending rhythmic pulses through the cortex, regulating synchronization. Rather than acting as a passive relay station for sensory signals, the thalamus functions as an active coordinator of global information flow. Cognitive control and decision-making are the result of this architecture, achieving a highly coordinated state of synchronization. We can ground this network theory by deconstructing a single experience, encountering a familiar object, like a hammer. The temporal lobe processes its visual shape and the characteristic sound it makes when striking a surface. Simultaneously, the posterior parietal cortex maps its tactile properties and the specific grip mechanics required to hold it. The hippocampus provides the memory of where the tool is kept, while the prefrontal cortex manages the goal, the anticipated outcome of driving a nail. When we look at the brain during this moment, We see disparate hubs in these regions flash in perfect unison, forming a single, unified network state. The hammer does not exist as a picture in one location. The representation is the coordinated activity of all these distributed systems acting at once. The nervous system organizes itself through an elegant biological hierarchy. This hierarchy is nested. Every level is simultaneously a component of a larger system and an organization of the smaller parts beneath it. The physical structure cascades upward from ion channels to neurons, microcircuits, populations, and local cortical maps. This gives rise to a conceptual ascent, from local maps to objects, categories, multimodal concepts, and finally, ongoing interaction with the world. This nested hierarchy describes the physical organization of the brain. Understanding this biological architecture is the first step. In the following chapters, we will examine how these principles of hierarchical integration might support the broader mechanisms of tokenization theory to explain how the brain realizes relevance.